Okay, and now the last portion of the Earth processes test. This is the short answer piece. All right, the questions on this part of the test deal with radioactive decay and the half-life of radioactive materials. So this first question talks about radioactive decay. The first thing I need to do is identify what kind of radioactive decay am I dealing with. It says right here that it is releasing a beta particle. So that is really important for us. When it says beta particle, then I know that the particle that is being emitted is an electron with mass 0, charge -1. If that said an alpha particle, then I would know that I was dealing with a helium with mass 4 and atomic number 2. But this is not the kind that we're dealing with right now, so we're just going to disregard that, but we want to keep it in the back of our head just in case we saw a different question on the retake. So this is a beta particle. And it says that we're dealing with carbon-14. So if it's carbon-14, then 14 is the mass number. And I'll look at my periodic table of the elements, which I've always got close by, and I can see that carbon is atomic number 6. So that's the number that I'm going to put on the bottom. And it is going through radioactive decay, and it is decaying into some material. I don't know what it is. That's the whole point of this question. So I'm just going to put a placeholder here. It's an X, and I'm going to mark the atomic weight as A and the atomic number as Z. We've got to figure those things out. I do know that it also gives off a beta particle. Now I can break this down into a couple of simple addition, subtraction, algebraic equations here to figure out what is A and what is Z. Then I can use those numbers to figure out what X is. So let's take the top part first. So I can break that down into 14 equals A plus 0. Now I just need to solve for A. So I'm saying that A or 14 equals A, and then this 0, just for the sake of doing the math, I'm going to pretend we're moving it around to the other side. And when we move it to the other side, we might say it's 14 minus 0, which of course is still 14. So A equals 14. Okay, let's do the same thing now on the bottom. So I can say 6 equals Z minus 1. Minus 1 because that's a negative number. Now I do the same thing. I can say 6, and I'm going to move the minus 1 to this side. When I move a minus number to the other side of an equal sign, it becomes plus. If this were an alpha particle question and I was moving that 2 to the other side, I would be subtracting it from this number. But because that's a minus, I'm moving it over and putting a positive sign on it. So 6 plus 1 equals 7, and that equals Z. So now I'm going to take my A number and my Z number, make sure that's a Z, not a 2, and I'm going to put those back into my original equation here. So if A is 14 and Z is 7, what is X? Whoops, 7, excuse me, 7. What is X? So I look back at my periodic table. Well, the 7 is the important part because that is the atomic number, and it's always going to identify for us what element this is. And we can see here that 7 is nitrogen. So this carbon turned into nitrogen. Now I'm going to write that, which answers part of the question, but I want to put this back into the equation so that I can really write out what was happening here. And that is that carbon-14 decayed into nitrogen and released an alpha particle, or excuse me, a beta particle. And there we go. We've shown our work by doing this. We've shown the whole equation with the unknown and with the mystery element in place. All right, let's look at the second question. Second question is basically showing us how scientists use radiometric dating, knowing the half-life of different materials that they might find in things like rocks or sometimes in carbon. In this case, we're dealing with potassium that decays into argon. And it's telling us that there is 1/16 of the original, like, complete amount of potassium-40 is remaining. It also tells us that the half-life of potassium-40 is 1,250 billion years. So every 1,250 billion years, half of whatever amount of potassium-40 I have has decayed into argon-40. Well, first, let's kind of look at that chart that we made in class of half-lives. So at 0 half-lives, I have the full amount, in this case, of potassium-40. I've got 1 out of 1. So this is just the definition of half-life. After 1 half-life, I have half the material. After 2 half-lives, I have half of half the material, which is 1/4. 1/2 times 1/2 is 1/4. After 3 half-lives, I have half of the 1/4 that was there before. So in that case, I would have 1/8. Half of 1/4, or 1/2 times 1/4 is 1/8. After 4 half-lives, I would have half of 1/8, which is 1/16. 1/8 times 1/2, 1 times 1, 8 times 2, 1/16. I could keep going. I could say that at 5 half-lives, I have 1/32. At 6, I've got 1/64, and so on. But this was what I was looking for, because it tells us in the problem that I have 1/16 remaining. So now I know that that means 4 half-lives have gone by. So 1/16 is 4 half-lives. That's part of what I need. Now I need to know, how long is 1 half-life? Well, it tells us that. That's a given, is that 1 half-life is 1,250 billion years. So 1 half-life is 1,250 billion years. So now it's a problem. So I'm saying if 4 half-lives have gone by and each one is 1,250 billion years, how much time has gone by? How old is this rock? Well, I mean, I can look at that as 1,250 billion, 1,250, 1,250, 1,250, right? 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, and I could figure out the sum of that. Or, of course, the easier way would be to say 4 times 1,250 billion years. Either way, I get 5,000 billion years, or 5 trillion years. And that's our solution. All right, and as always, studying has made this easy, so I'm going to say I'm giving this quiz a 1 now, because studying makes tests easy. Remember, when you're doing these problems, identify what kind of particle is being released, because that's going to determine the math for the rest of the problem. And identify how, based on the ratio of material that is remaining, how many half-lives have gone by. And if you know how many half-lives have gone by and how long one half-life is, then you can figure out how much time has passed. All right, thanks for hanging in there and good luck with your retake.